Howdy everyone, and welcome to the first video lecture for Accelerated Calculus. Welcome to our first look at finite and infinite series. Mostly today we'll be focusing on geometric series, which are, I would say, the most well-defined and easy to compute and just generally understood type of infinite series. We'll be looking at a few more general things with the next lecture when it comes to increasing and decreasing series, and then we'll begin to focus on specific ideas of convergence and specific ideas of what exactly we use infinite series for. But for now, let's mainly focus on probably the most common type of convergent series. Convergent infinite series, which is the geometric series. So we'll start by looking at some basic definitions of exactly what finite and infinite series even are, and then we'll move on to the geometric series. So first off, let's talk about understanding just what a series is. A series is essentially built from a sequence. It's the sum of terms in a sequence. So the sum of the first n terms is written S sub n, which is known as a partial sum. So if we have some sequence A sub n, then S sub 1 is just A sub 1. S sub 2 is A sub 1 plus A sub 2. S sub n is A sub 1 plus A sub 2 plus blah, 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 plus A sub n, which we can just write as the sum from k equals 1 to n of A sub k. So this is just adding together all the terms of a sequence. Neat. That's really, when we talk about a series, that's really what's going on. It's just a sequence with plus signs instead of commas. So a certain series. So let's talk about this. A certain series is the ordered sum of terms from the sequence. A sub n equals 0, 3, 8, 15, 24, 35, and so on. So let's find S sub 6. Side note, by the way I found this series was just n squared minus 1. But yeah, so here S sub 6 is just going to be the first 6 terms added together. So 0 plus 3 plus 8 plus 15 plus 24 plus 35, which I make out to be 85. And that's it. This is all we really need to do to find a partial sum. There's not really anything special here that's going on. This is going to be something we use implicitly inside other things that we do. So by itself, partial sums aren't particularly useful. They have their place, namely in, let's say, paying off annuities, namely in financial mathematics. Partial sums are a pretty big deal. Outside of financial math or other kind of geometric progression or projections, partial sums really aren't what we use, but they're necessary in terms of what we will need them for. So our reason that we need them, what we really use these for, is our quick note on convergence, which we will spend a lot more time on later. Those of you who have either seen or heard about the Taylor and Maclaurin series parts of Calc 2 know that, or at least would have heard that, this is an extremely detailed part of this course. So we are going to be talking about convergence in extreme detail later on, so we're not going to go into it very much here. We're instead going to focus on geometric series and the convergence thereof, because it's much nicer and easier and obvious. So anyway, quick note on convergence though, what it takes for something to converge, for what it takes for a series to be said to converge. If the sequence of partial sums converges to some L, to some limit L, then we say that the series converges and that its sum is L. So in other words, what we need is the infinite sum of all of the different terms in a sequence need to add up to L specifically. And the best way for us to find that is for us to say, well, is there a very, is there a diminishingly small change between S sub n and S sub n plus 1? And this is one of the principal ways that will define whether or not something converges when all else fails. Hopefully all else won't fail. We have plenty of other ways to help us out with that without having to resort to kind of final ideas of just desperately trying to make sure that things are convergent on a limit basis alone. But mainly here, what we want to focus on is this idea that the partial sums are really just here as a means to an end. Without further ado, we're just going to go ahead and talk about geometric sequences. We'll get into this more later. We'll talk more about specific techniques of convergence that let us avoid this. We'll see this in more detail later, so it's not worth spending time on right now, especially since this really isn't actually particularly relevant to geometric sequences themselves. So yeah, time for the main point of this slideshow. You can see we're on kind of the second informational slide here, and there's 9 informational slides, so you can guess what most of this is about. So yeah, we'll take a look at geometric sequences, which will then shortly become geometric series. So, geometric sequences. A geometric sequence is just a sequence of terms where every term is a constant multiple, the same constant multiple of a term before it. So in other words, a sub n is some constant multiple of a sub n minus 1 for all n. So we generally refer to this multiple as r. So what will happen is we'll have a first term of a and a multiplier of r. So our sequence will just be a sub n is just going to be ar squared, ar cubed, ar to the fourth, and so on. So a geometric sequence with the first term of 2 and an r of 3 is just going to be 2, then 2 times 3, then 2 times 3 squared, 2 times 3 cubed, and so on. You can see that computed out, this is just 2, 6, 18, 54. Each piece of this is 3 times the previous piece, right? 54 is 3 times 18. 18 is 3 times 6. 6 is 3 times 2. If there was something before 2, it would have to be 2/3. If there was something before that, it would have to be 2/9, right? But this, if there's not, the sequence starts at 2, but that, that would be the idea. So yeah, this is what a geometric sequence is. It's just a sequence where each term is a constant multiple of the term before it. So the main thing that we're going to need is we need 2 things. We need the first term, we need to know a, and we need to know r. If I know those 2 things, I know everything about this sequence. So finding a is pretty easy. I figure out where the sequence starts, and that's a. Neat. Finding r is perhaps not so obvious sometimes. Most of the time, it's pretty clear. I mean, I think it's pretty clear here that r would be 3, even if nope, let's put that back. I think it would be pretty clear that r was 3, even if I didn't tell you. But let's take a look here. So what we have is we have that we know each term is going to take this form, right? ar squared, all the way up through, ar n minus 1, or ar to the n minus 1, sorry, ar to the n, and so on. Well, if we take a look at this ar to the n minus 1, ar to the n, if I were to divide ar to the n by ar to the n minus 1, I just get r, right? The a's cancel, all the copies of r except for 1 cancel. There's 1 more r up here than there is down here. So literally, if I just take any two sequential terms and divide the later one by the earlier one, I'm going to get R, guaranteed. So I just pick any two terms in the sequence, any two terms next to each other in the sequence, divide the later one by the earlier one, and I've got R. So let's just consider this little four-term geometric sequence of 4, 0.16, 0.0064, 0.000256. And it doesn't matter which pair of terms I pick. I could divide 0.16 by 4. I get R equals 0.04. I could divide 0.0064 by 0.16. I get R equals 0.04. I could divide 2.56 times 10 to the negative fourth, or 0.000256 divided by 0.0064, and I get 0.04. Note, fractions, also appropriate. When I built this sequence, I was building it around R equals 1/25th, and then for a reason that will be lost to time, I wrote it as decimals. But yeah, fractions are also appropriate, so 1/25th is fine. I would even say fractions are often preferred. So yeah, this is it, right? The finding R shouldn't really be much of an issue. So let's take a look at taking these sequences and turning them into a series. So a geometric series here is just this idea of a sequence, right? AR squared, AR cubed. And then instead of just writing as a sequence, we're actually adding those terms together. So here what we have is the sum from n equals 1 to infinity of AR to the n minus 1. Sometimes you'll also see something that starts at n equals 0 and writes AR to the n. This is something that will be this is something that we'll use a lot when we actually get around to Taylor and Maclaurin series. But for the definitions that we tend to use for geometric series, it's cleaner for us to write it like this. So yeah, let's take a look at what's going on. Here, R can be any real number. You'll end up just with what's known as an alternating series if R is negative. Not a problem. It just bounces back and forth between negative and positive. And if and as I write here, if you only have numeric terms, you can see if a series is geometric by just checking if individual terms, as we saw, last slide, if this has a consistent value. And if it does, then that value is R. So we're not going to compare sums, but we're going to compare specific terms. Essentially, we're just following this particular slide. So this looks like a complicated sum. This does look like a difficult sum to compute. But we have a way to fix that. And that is that there's actually a closed form, meaning that I don't need to write an infinite sum out. I can actually just write out something in terms of only a bunch of constants and n. So there's a closed form for S sub n, and this closed form essentially is built algebraically. So I could start with this idea that S sub n is equal to, this sum up through the nth term. So AR to the n minus, S sub n equals this whole sum all the way up to AR to the n minus 1. And so what I do here is I can multiply both sides of this equation by R, and it gives me R times S sub n equals everything but, one order higher. But if I subtract the second equation from the first, I get S sub n minus R S sub n is equal to A minus AR to the n. Now, the reason for this is if I'm subtracting this from this, then all these terms from here to here are going to cancel with all of these. A doesn't have anything to cancel with, so it gets stuck there. AR minus AR squared minus AR squared, AR cubed minus AR cubed, blah, 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 AR to the n minus 1 minus AR to the n minus 1. And then there's nothing for AR to the n to cancel with, so we just get stuck with minus AR to the n. So here we have A minus AR to the n. is equal to S sub n minus R S sub n, based on essentially the left-hand side, based on the difference of the left-hand sides. And now just factoring out 1 minus R and then dividing by it gives us, and factoring out an A over here, gives us S sub n equals A times 1 minus R to the n over 1 minus R. And this is how we find a partial sum for a geometric series. It's a nice closed equation, no need to add a bunch of stuff together. You just plug in R, you plug in N, you plug in A, and you're done. So let's take a look at this. Here I just show an example of finding the third, fourth, and fifth partial sums for a geometric series with a first term of 5 and an R of 4. Now, it's not hard for me to compute these directly. I mean, at some point, it's not particularly easy either, but it's certainly doable. We start with 5 as my first term. My second term is then 20. My third term is then 80. 5 plus 20 plus 80 does equal 105. My fourth term is 320. Add 320 to that, you get 425. Perfect. And then 320 by 4 is 1280. Add 1280 to 425, you get 1705. Perfect. So these do mesh, but nicely I could have done that without needing to do a bunch of arithmetic. And if this instead were something like find the 12th partial sum, this might be nicer, right? So all we have here is S sub 3 is equal to A, which is 5, right here. Oops, right here. Times 1 minus R to the n, so R is 4, n is 3, over 1 minus R. And this gives me 5 times negative 63 over negative 3. And then for 4, instead it's negative 255 over negative 3. And then for 5, it's negative 1023 over negative 3. Now, side note, if R is a whole number, this particular equation will always be a whole number, other than, you know, whatever A is. It'll just be a whole number times A. A might screw it up, but 1 minus R to the n over 1 minus R will always be a polynomial in terms of R. You can either do that by kind of your basic rules of polynomial factoring. You can do that by basic rules of prime factoring. You can do that by brute force if you so choose. You can do that in a very elegant way later on using something using prime factoring and something known as Fermat's little theorem, which is a really amazing piece of logic that you learn in a little bit in number theory and a little bit in abstract algebra, but that's, you know, third year college, fourth year college stuff. But still, there are plenty of ways to show that if R is a whole number, then 1 minus R to the n over 1 minus R will also be a whole number. So as you can see here, right, like everything's whole numbers, as you might expect. If R isn't a whole number, then you end up with a polynomial in terms of R, so your answer will be some linear combination of powers of R, which is, you know, fine too. That's got its own results. Anyway, that aside, even in video recordings, random asides, you can ignore those 2 minutes if you want, or don't. I think it's neat, so I talked about it. Anyway, back to trying to look at what's going on here. I want to talk a little bit about infinite geometric sums, infinite geometric series. The essentially nth partial sum as n goes to infinity. So here, that's exactly what we're looking at. The nth partial sum as n goes to infinity. I wanted to actually grab that. There we go. This is exactly what we're looking at. So let's talk a little bit about where this is going to converge and where this isn't going to converge. So we've got a bunch of options here. We've got The only place where it converges, which is when the absolute value of r is less than 1. What this means is you are just essentially sitting there with r to the n. And by rules of exponents, when r to the n is treated as a limit as n goes to infinity, if r is less than 1, if r is somewhere between, somewhere strictly between -1 and 1, between -1 and 1 exclusive, then this power is going to go to 0. It has to, right? Like multiplying something that's below 1 by itself enough times eventually yields something infinitely close to 0. So what we end up left with is a over 1 minus r, which is definitely a real number and is exactly what the series will converge to. This is, it's kind of in small print despite its importance. This a over 1 minus r is the limit, is what a geometric series will always converge to. If you know a, if you know r, if the geometric series converges, this is what it converges to, always. And now let's look at all the different ways it could diverge. If the absolute value of r is greater than 1, well, then this grows exponentially by definition. So yeah, that's not going anywhere good. If r equals 1, then this is just 1. And you just end up taking an indefinite form, but you can either try and resolve this by factoring, by L'Hopital's rule, by this, that, or the other thing. It really doesn't matter. The point is that it's going to be clear that this is just the series is just going to be a added to itself a bunch of times over. So that is an infinite sum. It definitely diverges. Really nothing more needs to be talked about. And then finally, when r is -1, you might not have an infinite sum, but the limit certainly doesn't. Exist. It's oscillating in a discontinuous way. It's just bouncing back and forth between a value for when r is odd or a value for when it's essentially a when n is odd, or 0 when n is even, or what have you. So it's again, by observation, this is just not convergent because it doesn't go to a single value. So yeah, only place where we converge is when the absolute value of r is less than 1. This is the only time a geometric series converges. You needn't worry about any others. So let's take a look at some examples of geometric series here. So let's just try and figure out what these converge to, even though all the answers are right here. So what we start with is the series defined by a sub n equal to 1/3 to the n plus 1. Notice here that when n is 1, a to the first isn't 1/3, it's 1/9, because it's 1/3 to the n plus 1. So a sub 1 is actually 1/9. But other than that, r is obviously 1/3. I mean, every single time n increases, we're multiplying by another copy of 1/3. So r is clearly 1/3. So we get a equals 1/9, r equals 1/3. So the series converges to 1/9 over 1 minus 1/3, which is 1/6. And done. Another way we could look at a sub n equals -1 to the n minus 1. This is just a straight definition of what's going on here. It's just r. We straight up just have r to the n minus 1, -1 to the n minus 1. This is this exact example by definition. So it's divergent. And in fact, what's going to happen here is it's going to bounce between 1 and 0. Finally, we've got 4, -2, the series, or the sequence rather, 4, -2, 1, -1/2, 1/4, presumably -1/8, 1/16, and so on. So here we get a equals 4 because it's the first term. Nope, don't want it bold. We just get a equals 4. Neat, it's right there. And here we can find r just by taking any term and dividing by the term before it. So here, you could take 1, divide by -2, you get -1/2. You could take a -1/2, divide by 1, you get -1/2. You could take 1/4, divide by -1/2, you get -1/2. It doesn't matter what you do. No matter what, you're going to get r equals -1/2. So here, it's r equals -1/2 is definitely has an absolute value below 1, so it's definitely convergent. So here the series converges to, there we go, converges to 4, which is a, over 1 minus r. So 4 over 1 minus -1/2, or 4 over 3/2, which is 8/3. Neat. So very last thing here, this is the last piece of information, and then I'll go to a whiteboard and do some examples. There is, or do a couple more examples at least. There is something we're going to be focused on later on, which is a kind of a big deal, which are intervals of convergence. And it's places essentially where we could say like, oh yeah, no, this series does seem to converge, versus an interval where it's like, oh no, this just shoots off toward infinity. And we'll learn more about that later. But it's worth doing right now while we're learning geometric series, because it factors in quite nicely. Just to see these for the first time. So here, what we could do is, if we have something that's clearly an infinite geometric series, but it's got a composed function, we can still determine in terms of the variable of our function where it will converge. So if r is supposed to be, if whatever we have to like the n or the n-1 or whatever is supposed to be an absolute value less than 1, because that's the only way it will converge, then we just replace r with whatever here is being raised to the n, or the n minus whatever plus whatever, or the 2n, as the case may be. It really doesn't matter. Whatever's being raised to a power that's creating a geometric series, that's going to be how we figure out where it converges or doesn't converge. So -2x is effectively r here. So if we have that it should converge when absolute value of r is less than 1, then we need to just check absolute value of -2x less than 1. So that means -1 less than -2x less than 1, which when we divide everything by -2, we have to flip the signs. We get 1/2 greater than x greater than -1/2. So if x is in here, the series converges. That's it. That's how we find intervals of convergence for geometric series, at least. So let's just look at one more. It's just algebra, right? So once again, we pick what our r is going to be. And here, once again, if I just wrote like -5, it doesn't matter. It's still r. If I wrote +3 or +2, it doesn't matter. That's still r. The only way this would matter is if I made this a 2n, then this squared is r, right? But that's not what's happening here. We just have a pretty simple like to the n. So anyway, once again, if x minus 1 over 4 is supposed to be our r, then we just need that x minus 1 over 4 is less than 1. But then that means that -1 is less than x minus 1 over 4 is less than 1. So multiplying everything by 4 gives us -4 less than x minus 1 less than 4 gives us -3 less than x less than 5. And that's it. Job done. If x is somewhere in here, then the series converges. If x is anywhere else, it diverges. And yeah, so that's how we find kind of your basic interval of convergence for a geometric series. So without further ado, let's just look at a couple more examples of using geometric series, of using kind of the different pieces of machinery that I'll be asking you to do tonight or tomorrow night, as the case may be, or tomorrow afternoon at least, or well, before the next assignment is due. So let's pop over to a whiteboard here, and we'll take a look at a first series. So let's consider this series, or sequence rather. Let's consider the sequence 2, -10, 50, -250, 1250, and so on. So, forgive my handwriting, by the way. It turns out that I don't have a nice touchpad for this, and so I have to write with a mouse, and holy God, the people on Khan Academy make it look a lot easier than it is to do this. Maybe they're using a drawing tool instead of a mouse. Anyway, one of the first things we look at then is, well, if we need to treat this like a geometric series, what's our A and what's our R? So here, A, well, A is just the first term, so A is 2. Neat, done, found A, we're just the best. So here, the next thing we can do is we could just say, well, I need R, and by observation, I hope that anyone watching this slideshow would realize that R here is -5, just by observation. Every single time we move from one term to the next, we're multiplying by -5. But if you needed to check, I mean, something like 50 over -10 seems like a good bet, and yeah, sure, that's -5. Again, here I'm telling you the sequence is geometric, so you don't have to be like, oh, I need to check all the terms and look for a pattern. Generally, you can tell if you're not told if something's geometric, if there's a pretty obvious pattern that doesn't seem to be stopping, you can generally assume it is. But I'm not going to do that to you. If something's supposed to be geometric, I'll tell you it's geometric. Or I'll provide it in a format that forces you to assume it's geometric. I'll give it to you in a format that looks like this, right? Like I'll give it to you in a format that forces you to assume it's geometric just by actually looking like this. So going back to dealing with other things I might ask you, I might say, all right, well, what then is S sub 6? And here, if we want to find the sixth partial sum, what we have to do is we just have to say, oh, well, this needs to be A, which is 2, times 1 minus, and instant regret, 5 to the 6th over 1 minus 5. I regret life choices right now. And so if we need to deal with 5 to the 6th, I also regret not having a calculator. 25 by 625 is 15,625. So this is going to be 2 times negative 15, 6, 24. We over negative 4. So this is just going to be 7812. So yeah. There's our S sub 6. Neat. Remind me not to do that again. So pushing on to the next idea here. We might want to then look into we might want to look next into exactly what we need to deal with to have oops, mistakes were made. Backtrack. I forgot that R is -5, not 5. So we've got a couple of things to undo here. That is this. Watching me make mistakes live here. I'm glad I checked that because that doesn't make sense. All right. Simple enough to fix though. Oops, missed a line. There we go. All right. That I feel significantly better about that. So instead, we get something I feel significantly better about, which is negative 5208. Okay, there we go. That fixes it. All right. So careful there. When you have R's that are negative, it's very easy to lose a sign. You just watched me do it live, sort of live. But yeah, so careful about negative R's. If you do have a negative R, be sure that you're raising the entirety of R, so -5 to the 6th, and then subtracting the entirety of R, so 1 minus -5, so 6, not -4. So my previous answer would have been correct if R was 5, but R wasn't 5, R was -5. Anyway, that's it for kind of the first example here. If I instead wanted to ask you what if I instead wanted to ask you kind of what the infinite sum is, so you can write this as S sub infinity if you want. Everyone's going to understand what you mean. It's sort of commonly accepted notation. Any ideas what this is going to be before I reveal the answer? That's right. It's divergent. Unless you didn't think it was divergent, in which case, no, that's wrong. It's divergent. So the reason it's divergent is quite simple. Stuff keeps getting bigger. Um, R is the absolute value of R rather is above 1. So yeah, it's divergent. Let's take a look at another example. Let's take a look at this one. let's make my writing less incompetent. There we go. So here we've got 20, 5, 5/4, 5/16. Once again, relatively easy to figure out what A is. And at this point, R, hopefully it's very clear that we seem to be continuously dividing by 4. Recall, in the words of my old Russian math professor, who I quite like to quote, in math we do not divide things. So once again, we're not really dividing by 4 so much as multiplying by 1/4. So R here is 1/4. So what we end up with is A equals 20, R equals 1/4. If I wanted something like, say, if I wanted something like, let's say, S sub 3, because I'm going to save myself some trouble this time, I could easily just go ahead and be like, oh, look, it's 105/4. But I can also just say, well, it's got to be 20 times 1 minus 1/4. That is, yeah, we'll make it better. The third over 1 minus 1/4. And what we end up with here is 20 times 63/64, or negative 60, or yeah, 63/64 over 3/4, which would give you 20 times 21/16. But then, of course, that gives you 5 times 21/4, which is, of course, 104, or 105 rather, over 4. Neat. Now, if I ask you this time for, that's the worst infinity anyone's ever written. I don't even like infinity. If I ask you this time for the infinite sum, this time it's got 1. The absolute value of R is less than 1, so this works. 20 over 1 minus 1/4 gives us 20 over 3/4 gives us 80/3, and we're done. There's the infinite sum. That was fast. So all this, and we just have a nice easy sum of 80/3. Just the series converges to 80/3. Job done. It's super clean, right? And the interesting thing here is it doesn't converge. It converges to something that we couldn't possibly get to, right? And that's fine. There's no way, all my fractions are multiples of 4. There's no way for me to get to a third. And yet that's what it converges to. But that's okay. It's not that we're actually trying to get to that number. It's that we need to be infinitely close to that number, and that will happen. So yeah, this is it. This is how we would handle something like this. So let's take a look at one final example, and then we'll call it. Let's take a look at this. The sum from n equals 1 to infinity. Let's make that look a little less terrible. Let's go with a number we don't see that much in my class. So let's take a look at this. First off, we've got some constant times some function to the n minus 1. So this is taking the form, sorry, of a geometric series. We can treat this like it's geometric because it is. Whatever x is, this is going to create a geometric series. So here, it doesn't really matter where this starts. I could start this at n equals 4, and it would do the same thing. I could start this at n equals 11. It would do the same thing. I could start this at n equals 0. It would do the same thing. It doesn't matter. Similarly, it doesn't matter that this is n minus 1. It could be n minus 100, and it wouldn't matter. The point is that I've got something being raised to a power of n. So, to the power n, rather. So all I need to do here is I just need to treat this like it's r. So what I need is 2x over 5 plus 7. Try that again. Has to be less than 1. In other words, negative 1 is less than 2x over 5 plus 7 is less than 1. In other words, negative 8 is less than 2x over 5 is less than negative 6. And then finally, in other words, there we go. Negative 20 is less than x is less than negative 15. And that's where this geometric series converges for any x between negative 20 and negative 15 exclusive. And that's it. Just algebra to solve for an interval of convergence. Just use algebra. So that's all for now. That's about all you need to know about geometric series for the purposes of this class. So, yeah. Thanks for listening, and the next things will, talk to you soon.